So for the first part of this question, we want to prove an equivalence. The first direction we shall prove with the contrapositive. Suppose that naught is an element of C. For all vectors eta in Rm, it clearly holds that eta product with naught, the zero vector, is equal to naught. Thus, for any eta in Rm, the infimum of the product of eta and C, for C in C, is less than or equal naught. Because we know that at least there is one vector C for which it is equal naught, and the infimum should be less than or equal that. Taking the contrapositive yields the result. So that is that if there is some eta for which this infimum is greater than 0, then naught is not an element of C. Now for the other direction. That first direction doesn't require any additional assumptions on C, not that it's closed or convex or anything like that, but this direction does. Suppose that naught is not an element of C. Since C is non-empty, closed, and convex, so is the set minus C, which is just the set contained of all the vectors of C, but multiplied by minus 1. In addition, naught is not an element of minus C. Now we should prove something for minus C, and from that obtain our result for C. The separation theorem gives us the existence of a linear map L from the set of vectors Rm to the real numbers, and a constant gamma in the reals, such that L applied to any vector C is less than or equal gamma for all elements of minus C, and L at 0 is greater than gamma. Since L is a linear map, we can express it in terms of product with a vector, that is, there exists an eta in Rm, such that Lx equals eta product x for all x vectors in Rm. Therefore, if we call this equation up here star, star can be written eta product C is less than or equal gamma for all C in minus C, and gamma is less than 0, which immediately gives that eta product C is less than 0 for all elements of, minus capital C. This is for this one particular value of eta. It therefore follows that the supremum of eta product C for all C in minus C is less than 0. Less or equal 0? Less than 0. No, less than 0, of course, because they're less than or equal gamma. So the supremum is less than or equal gamma, and that is strictly less than 0. So the supremum is strictly less than 0. So actually this implication here is slightly weaker. It's a bit misleading. What we need is the result above it. Thus it follows, now writing this in terms of C instead of minus C, that the infimum of eta product C is greater than 0. And we have what we wanted to prove. Now for the second part of the question, we should suppose that D is bounded and that D and E have no common elements. I shall define a new set, E minus D, given by the difference, given by vectors which are the difference of elements of E and D. What we shall prove is that this set E minus D satisfies the conditions of part A, and then use part A to prove the result. Since E and D are non-empty, so is E minus D, of course, since both E and D have at least one element in them. Since D is bounded and E and D are closed, E minus D is also closed. This here is the only place in which we need the assumption that D is bounded, but it is necessary for this assumption, otherwise E minus D may not be closed. Since E intersect D is empty, 0 is not an element of E minus D. That one's straight from the definition. And then finally we can show convexity for two distinct elements of E minus D and lambda between 0 and 1. The convex combination of these elements, just linearity, is equal to the difference of the convex combination of the individual parts. Since E is convex, the first part is contained in E. Since D is convex, the second part is contained in D. And so, because we're taking the difference, the whole thing is contained in E minus D. So we have this set, E minus D. It's non-empty, it's closed, it's convex, and it doesn't contain 0. Now, we can apply part A to E minus D to see that there exists an element, a vector, eta in Rm, such that 0 is strictly less than the infimum of eta product of x for x in E minus D. This we can rewrite eta product E minus eta product D for E in E and D in D. That's just by definition. And since we're taking a difference here and the infimum over all possibilities for E in E and D in D, this infimum is just equal to the minimizer, the infimum of eta product E minus the supremum, the largest possible, of eta product D. This whole thing is greater than 0, and we therefore get what we wanted, which is that the supremum whoops, that should be a D, of eta product D is strictly less than infimum eta product E.